Welcome to Quantum Field Theory. I'm your host, Bari, and I'm very excited to guide you along this journey of QFT. Now, what exactly is QFT, Quantum Field Theory? Well, it's a marriage of two completely separate branches of physics. One is special relativity, Einstein's theory of what happens when things move fast, and the other is quantum mechanics, Niels Bohr, Heisenberg, Pauli, Schrödinger, Dirac, their theory of what happens when things go small. So you combine the theory of what happens when things go small with what happens when things go fast, they don't seem to mix. So the first thing we're going to start with is a simple thought experiment proposed by Niels Bohr that shows that regular non-relativistic quantum mechanics just doesn't cut it when it comes to special relativity. So here's the thought experiment. First, we start off with a box. Here's my box. And this box has an electron confined inside of it. It's a perfectly reflecting box so that if the electron has sufficient energy, it still cannot tunnel out of the box. Of course, that's not pragmatic experimentally, but that's the situation we have here. We have an electron confined to a box. Now, of course, this box has some kind of a length. Okay, I'll call it L, whatnot. Here's the thought experiment. Start shrinking the box. What happens? Well, at some point you will reach the de Broglie wavelength of the electron. Okay, in other words, you will start localizing the position of the electron as you decrease the length of the box. But hang on a second. Werner Heisenberg came up with this uncertainty principle telling us that we can't exactly locate where the electron is because we'll have to pay a price in the form of the uncertainty principle. The uncertainty principle says that as we squeeze the box, as we localize the position of the electron, the momentum goes to hell. In other words, delta x is proportional to 1 over delta p. As the uncertainty in the position decreases, the uncertainty in the momentum increases. And at some point, the uncertainty in the momentum is going to be huge. Well, why is that a problem, though? Well, Einstein comes along and gives us his dispersion relation. Of course, we all know that E is equal to mc squared, but there's the second part that we don't know. This is, of course, just the rest energy, but the energy due to the movement of a particle is coming in the form of its momentum, and so that's what we have here. And now if I square all of this, now I have Einstein's dispersion relation. And this tells us that as the momentum increases, as the uncertainty in the momentum increases, at some point it'll be much greater than the rest mass of the electron. What's the problem with that? Well, the problem is when the uncertainty in the momentum gets too huge, well, then the total energy of the electron will become too big. And because energy is equivalent to mass, when the energy of the electron becomes too big, we no longer know if there's one electron or two electrons inside the box. In other words, when the electron's energy becomes enough for there to be two electrons in the box, then we have essentially created a particle antiparticle inside of this box just by squeezing the box. Moral of the story, just by shrinking a box with an electron inside of it, we have started to create particles inside the box. How wild, how crazy is that? Well, remember that at the very beginning, when we just had this single electron, we had a wave function, some kind of a wave function psi, describing all the properties of this electron, including its position, momenta, whatnot. So when we squeeze the box and increase the momenta, increase the energy of the electron, and thereby create more electrons inside the box, we suddenly have more particles to describe. But we started with just one wave function. How can we describe all the other particles just using this one wave function? That's not what we set out for. This is kind of like setting out to buy something at the grocery store, but when you actually pay for it, turns out it's a scam. You didn't buy what you paid for, right? Here we had a wave function which was meant to describe just one electron, but once we shrink the box, we've got more particles. Our wave function can only describe the original electron. It can't describe all the new particles that have come into existence by virtue of us squeezing the box. So That's the problem. That's Niels Bohr's thought experiment, which showed that regular quantum mechanics is insufficient to handle special relativity. So then, two young gentlemen named Klein and Gordon, and actually Schrodinger before that, but Klein and Gordon came up with a proposed solution to solve this problem, to reconcile special relativity with quantum mechanics. Let's go ahead and derive the Klein-Gordon equation. So here's the Schrodinger equation in its time-independent form. H psi equals E psi. Now, you might see this as a kind of conservation of energy equation, right? We've simply got the Hamiltonian on the left side and the total energy of the particle on the right side, right? That's just an eigenvalue equation. So now comes the idea of combining this with Einstein's dispersion equation, which says that E is equal to mc squared plus the momentum component pc. Now let me just square these, and we have Einstein's dispersion relation. Now you might remember from quantum mechanics 1 that we replaced momentum with the following operator, minus IH bar partial x, or if I were to generalize it even further, minus IH bar times nabla, the spatial derivative. We can do the same thing, but now with energy instead of momentum. For energy, instead of replacing it with a spatial derivative, let's replace it with a temporal derivative. Okay, and now let's see what the dispersion relation becomes. Okay, so I'm going to replace E squared with what? Well, if I square this, then E squared is equal to, I have IH bar partial t. And by the way, for all of you freaks out there who are fidgeting because I'm not using natural units just yet, I'll be using natural units at the very end where H bar and C are equal to 1. So no worries. So here I have E squared is equal to minus H bar squared partial T squared. So here's my E squared. What about my P squared, since I'll need it at any point? P squared is equal to, just square this, so minus IH bar nabla squared. And this is equal to I squared, which is minus H bar squared nabla squared. Okay, very good. So I've got my E squared and P squared. Now I can combine them to form the quantum mechanical dispersion relation. So I'm going to have minus H bar squared partial T squared is equal to mc squared. Okay, so I've got m squared c to the fourth, and then plus p squared, which is simply minus h bar squared nabla squared times c squared. Okay, very well. Now, of course, none of this really makes sense if we don't use a wave function for this entire thing to operate on. So let's introduce a wave function phi for both sides to act on. So I'm going to have minus h bar squared. Oh, I was going to write 2m, but I don't have an m right here yet. So I'm going to write minus h bar squared partial t squared phi is equal to m squared c to the fourth minus h bar squared nabla squared c squared. Now, using natural units, h bar squared is gone. Oh, and so is my chalk, apparently. So is my chalk. So h bar squared is gone, c to the fourth is gone, c squared is gone, h bar squared is gone. And now we're very close to the Klein-Gordon equation. If I go ahead and do some gymnastics here, seems like I forgot the phi over here, so apologies. So now, if I go ahead and move this over to the other side, I've got partial squared phi partial t squared on the left-hand side, which is apparently not visible in the camera anymore. So I'm going to write it over here. So partial squared phi partial t squared is equal to, on the right-hand side, actually I've moved it to the right-hand side, so this is going to be minus nabla squared phi plus m squared phi. And all of this is equal to 0. So now we have arrived at the Klein-Gordon equation. Believe it or not, it was literally as simple as that. Okay, so minus nabla squared plus m squared. Just factor out your phi, and voila. There's your Klein-Gordon equation. If you want to be a bit fancy, then some physicists define this little thing over here to be the d'Alembert operator. So let me clarify that here. The D'Alembert operator, this little squared, is defined as partial squared partial t squared minus nabla squared. So that simplifies our expression to nabla plus m squared acting on phi gives us 0. The reason that most physicists separate out this this D'Alembert right here is because it's pretty special in terms of special relativity. This guy right here, the D'Alembert, is a relativistic invariant. Relativistic invariant. That means if you switch reference frames, this quantity stays the same. It's just like the space-time interval doesn't change between inertial reference frames, neither does the D'Alembert. It changes just like a scalar, aka it doesn't change at all. So the D'Alembert transforms like a scalar, aka it doesn't change, it's an invariant. And mass, of course, is a scalar. Okay, so that means the D'Alembert plus the mass is going to give you a scalar function, right? This right here, this whole thing right here is a scalar acting on phi to give you 0. So this right here is our Klein-Gordon equation. Now, why did this fail? Why did this not win the Nobel Prize? Why did Dirac scoop the Nobel? Well, the reason why this failed is for a rather trivial reason. It's because it gives rise to negative probability densities. In fact, that's why Schrödinger himself created this equation and then discarded it. It gives rise to not only negative energies, which is okay because we can have bound states in quantum mechanics, but it also gives rise to negative probability densities, which is an absolute no-no in quantum mechanics. So let's go ahead and check out why it gives rise to negative probability densities. Now, for a long time, I didn't know where Einstein's dispersion relation came from. E equals mc squared plus bc squared. For a long time, I was scared to even ask. I thought it might have been an obvious answer. But it turns out Einstein's dispersion relation comes pop right out of the Klein-Gordon equation. Let's check that out right now. First, let's start off with the Klein-Gordon equation, okay, which, let me just remind you, is incorrect. It gives rise to negative probability densities, but it is a nice case example of how to reconcile quantum mechanics with special relativity. So let's start off with the Klein-Gordon equation. We have D'Alembert plus another scalar, mass, applied to some wave function gives us 0. All right, now the best physicists, what do they do for phi? What do they guess for the wave function? Well, they guess some kind of a free particle. All right, that'll make our lives easy. So let's say our wave function phi is some kind of a free particle. Okay, it's a function of space and time, and it's something like this, e to the I p dot x. Okay, so this is our guess for a wave function, right? So now what we're going to do is apply this guess to the Klein-Gordon equation and see what we come up with. So first thing I'm going to do is recall that the D'Alembert itself is defined as, let me look back, okay, so D'Alembert is partial squared partial t squared minus nabla squared. So this is the D'Alembert, and now we're going to apply this D'Alembert to our guess for a wave function. So let's do that. First of all, we're gonna work in just one spatial dimension, keep things simple. So keep it simple, stupid. So we're gonna have partial squared partial t squared minus partial squared partial x squared applied to this graft of a wave function, e to the I p dot x. Now, first of all, what is p dot x? Well, let's calculate that here. P is some kind of a 4 vector consisting of energy and the actual vector components of the momentum vector. In other words, P is a 4 vector consisting of the energy E, which is a scalar, and the 3 components of the momentum vector. Likewise, what is my other variable? X is a vector consisting of time and the actual spatial coordinates x, y, and z, as usual in special relativity. So that means when I take the dot product of p with x, I'm going to get et minus the dot product of these two vectors for momentum and position. So now let me bring this over here, I'm going to have partial squared partial t squared of e to the I et minus px. Px is, the dot product here is just px because I'm just working in one spatial coordinate, minus partial squared partial x squared, because I have the Laplacian right here, of e to the I et minus px. So first of all, let's take the temporal derivative right here. That's going to give rise to, let's see, let me just work this one out right here. That's going to give me IE e to the I et minus px. So first, that's the first temporal derivative's result. But now let's take the second temporal derivative. That's going to give me minus I, wait, no. So I'm going to get another factor of I, another factor of e. So that's going to give me minus e squared. And this right here is just our original guess for the wave function. So minus e squared phi. And then likewise, let's apply the same kind of logic over here for the Laplacian acting on our guess for the wave function. This is going to be, take out the minus ip, so minus ip e to the I et minus px. Now take the Laplacian once more. So I'm going to take partial x. So this is going to give me another factor of minus ip. So minus and minus gives me plus. I and I gives me -1. So I have minus p squared times the original guess for my wave function. So now I have minus e squared phi minus p squared phi. Don't forget there's a minus between these two guys, owing to the fact that we have the D'Alembert as the temporal derivative minus the Laplacian. So this is going to be minus this. And finally, what is all of this equal to? Well, this is all plus m squared, okay, plus m squared phi is equal to 0. So now let's simplify this, okay? Let me bring it over here, bring the action for the left side viewers. So we're going to have minus e squared plus p squared plus m squared is equal, times phi is equal to 0. Now you might already see the dispersion relation, Einstein's dispersion relation here, but let me really write it out explicitly for pedagogical purposes. And finally, if I just write this down as an eigenvalue equation almost, then we have the following. And so not really canceling out phi from both sides, but if I just take a look at what's on the parentheses in both sides, then I'm left with Einstein's dispersion relation that e squared is equal to p squared plus m squared. Not looking familiar? That's okay. Just remember that E is equal to mc squared plus pc whole squared, whole squared, whole squared. That means that e squared is equal to m squared c to the 4th plus p squared c squared. In natural units, c is 1. So we're just left with e squared is p squared plus m squared. E squared is p squared plus m squared. So we have indeed recovered Einstein's dispersion relation from the Klein-Gordon equation. But where are the negative energies we were talking about? Well, if I go ahead and square root both sides, this is actually kind of funny. See, hopefully you can see what I'm going to write here. If I square root both sides here, I get e is equal to plus minus the square root of p squared plus m squared. Where did that minus sign come from? Well, it came from considering the negative solutions once we take the square root. So there's something deeply weirder. It's that we have negative energies. But negative energies are perfectly fine because we're allowed to have bound states in quantum mechanics, right? You have negative 13.6 electron volts in the hydrogen atom's ground state itself. So what's the bother? Well, if you go a little bit further, as we will right now in a couple of minutes, we'll see that the Klein-Gordon equation also gives rise to negative probability densities. And that is something that you can't wiggle out of. Right, so the first step in showing that the Klein-Gordon equation gives rise to negative probability densities is to start with the probability current density equation right there. Now, if you're an absolute genius like me, then you don't need a reminder for where this comes from. But if it's been a few months since you last did quantum, then that's okay. Let's go ahead and derive this guy from first principles. So the first thing I'm going to do is consider an electron. Let's say you have an electron that's in some kind of a region. Maybe it's a free electron. And we want to figure out the probability that the electron is between x equals a and x equals b. Well, the electron has some kind of a wave function. This is a graph of psi versus x. The electron is going to have some kind of a wave function, right? And after some amount of time t, maybe this wave function has moved on. Maybe the electron has moved on to the right. Here's the question. What's the probability that you find the electron between A and B? Well, this is an elementary question for any quantum 1 physics student, right? All we have to do is write the probability that the electron is between A and B is the integral from A and B of psi squared dx. Voila, that's it. Now, how does this thing change? How does the probability change as the electron moves? That's a good question, you say. Well, first of all I have to do is take the derivative, temporal derivative of this probability, dp dt. And so that's going to give me d dt of this integral from a to b. But of course, I know that the magnitude of psi squared, well, I can just write that as psi conjugate psi dx. Okay, so now it comes time to take the product rule, right? Once I apply this derivative. So if I apply this derivative, then I get the integral from a to b. So I applied it to first psi star. So I get d psi star dt times psi plus, then I apply it to psi, d psi dt dx. Okay, very good. But now it seems like we're stuck at a dead end. But Schrodinger comes along and saves us. Remember that Schrodinger's equation tells us that minus h bar squared, not working in natural units yet, the Lord save me, tells us that the following is true for the time independent Schrodinger equation. So if I were to go ahead and look at this, then I would say that is of absolutely no help because there's no temporal derivatives in the time independent Schrodinger equation. So let's resort to the time dependent Schrodinger equation. Now that's much better. Okay, I always write it like this at first just to remember what it is, and then I actually expand it out. Because as you may know, I have very terrible memory. So minus h bar squared over 2m partial psi plus v psi. All right, there we go. All right, so now what does this tell us? This tells us what d psi dt is, right? If I go ahead and just solve over here, then I get divide by h bar on both sides. So first of all, we're going to deal with a free particle, right? So this potential right here is 0. Make your life as easy as possible, folks. That's the moral of the story when it comes to physics. So we're going to have IH bar times the temporal derivative of the wave function is minus h bar squared over 2m times the Laplacian of the wave function. We're just in 1D. So now if I go ahead and take out a factor of h bar from both sides and divide by I, then remember that 1 over I is equivalent to I over minus 1, aka minus I. So this gives us that psi dot is equal to minus I h bar. Oh, wait, there's already a minus sign here, so it'll just be minus minus, which is 1. So I h bar over 2m partial squared psi partial x squared. And likewise, for the conjugate of the wave function, we're going to have psi conjugate dot is minus. Now, you got to be careful with your minuses here because we're taking the conjugate here. So minus IH bar over 2m partial squared psi star over partial x squared. So now we can go ahead and plug this thing into our integral. So go ahead and do that. So the integral from a to b. So instead of d psi star dt, we have this monster. So we're going to have minus IH bar over 2m partial squared psi star partial x squared times psi, okay, plus psi star times d psi dt. So d psi dt is right here. namely it's IH bar over 2m partial squared psi partial x squared. And on top of all of this, we have a dx out front. So now the deal is done. So let's go ahead and factor out the IH bar over 2m. Okay, let's go ahead and factor that out. IH bar over 2m, just a constant out there. And so we're going to have minus partial squared psi partial x squared psi plus psi star. Oh, I factored that out, so no need to write it. Partial squared psi conjugate. Wait, that's just psi divided by partial x squared dx. Alrighty. So now the next thing to do is to stare at this for a while and then have a brilliant idea, namely that this entire thing can be rewritten as, first of all, let me factor out that minus sign real quick. So, okay, voila. This entire thing can be rewritten as the derivative of something. Namely, we can write this as the derivative, the dx, of psi partial psi conjugate partial x minus psi conjugate partial psi partial x. Now, if I was a professor, I would say this is left as an exercise to the reader. But I am not a professor, not yet, not for a couple more years, so I have to actually show that this is true. Because everyone will say, prove it, right? How do you indeed show that this is equal to that? Well, just work it out, okay? So let's go ahead and take the derivative as claimed, as proposed. So take the derivative here. I'm going to get d psi dx d psi star dx, whatever, partial derivatives, full derivatives, don't kill me if you're in the audience, plus psi d squared psi conjugate dx squared minus d psi conjugate dx d psi dx minus d minus psi conjugate d psi star, no, d squared psi dx squared. All right, so we've got this jargon right here. And notice, first thing off the bat is that these two terms cancel out. We're left with what I claimed, okay? So indeed, this does check out. And so now, this right here, in fact, is the probability current, or probability current density, whatever it's called. So this right here is J, what we tried to derive at the very beginning. Now, yes, there's a few minus signs, a few things that are offbeat, but more or less you can see we have psi times the spatial derivative of psi conjugate minus psi star times the spatial derivative of psi. So there you go. That's how you derive the probability current density, plus minus a few signs, whatnot. So now what we're going to do is show that the Klein-Gordon equation gives rise to, believe it or not, negative probability densities, or as we like to call it, heresy. All right, so how do we show that the probability density is negative, probability current is negative for the Klein-Gordon equation? Well, let's start off with the Klein-Gordon equation, which says that the D'Alembert plus the mass squared, all things a scalar, applied to a wave function is 0, where the D'Alembert is simply the second order temporal derivative minus the Laplacian squared. I mean, the Laplacian is the Laplace squared. All right, what am I talking about? All right, so that's what we've got so far. How do we apply it to show that the probability density is negative? Well, we start off with a continuity equation, which says simply that probability density is just like current, just like fluid, right? It's conserved in the form that the change in the probability density is equal to how much it changes over space. In other words, another way to write this is that the temporal change in the probability density plus the probability current is equal to 0. Sorry, this should be a spatial derivative. So now what we want to do is figure out what this partial j partial x is. Well, we've got j right here, but let's just take the derivative. So partial j partial x means just taking the spatial derivative of this probability current. So that's going to give us first minus I partial psi star partial x partial phi partial x minus I phi star partial phi x squared, and then plus I partial phi partial x partial phi conjugate partial x, and then plus I phi partial squared phi partial x squared. Alrighty, wonderful. So now what we've got is two terms that cancel out right here, and we're just left with these guys right here. Hopefully I did not screw something up. I took the derivative of this the second time, so there should be conjugate right here. So that tells us that partial j partial x, the derivative of the probability current, is equal to, factoring out an I have phi partial squared partial phi conjugate partial x squared, that's my first term, minus phi star, the psi conjugate, partial squared phi partial x squared. So I've got this whole thing, and now I'm going to plug it in right here. Or am I? Well, I can exploit the Klein-Gordon equation to my benefit, because if I just work in one spatial derivative, in just one spatial coordinate, then this Laplacian becomes this. And so my Klein-Gordon equation actually tells me something pretty useful. It tells me that partial squared partial t squared, let me use my Hagoromo so you can actually see what I'm writing, minus partial squared partial x squared plus m squared, all applied to phi, is 0. So that means partial squared phi partial t squared, this temporal derivative right here is equal to, let's see, is equal, plus m squared phi is equal to my spatial derivative. So in other words, I can replace my spatial derivative, my second order spatial derivative, with this temporal derivative term. So that's exactly what I'm going to do. Okay, replace these spatial derivatives with their temporal forms. Okay, hopefully you can see all the way up to here. Okay, great. So that tells me that partial j partial x is equal to I times. So I have phi times the second derivative of phi star. So that's just going to be partial squared phi conjugate partial t squared plus m squared psi conjugate. Okay, so that's there, minus phi conjugate, and then I have the same exact thing, but now with phi instead of phi conjugate, right? So I'm going to have partial, what am I doing again? I'm replacing this second order spatial derivative with this temporal derivative right here. So that's just going to be partial phi partial t squared plus m squared phi. And voila. So now I've got this for my partial j partial x. So now what are we going to do? We're going to take this and plug it in right here, so we can figure out what the probability density is. So partial rho partial t, the change in the probability density is equal to this mess right here, which actually simplifies once you realize that two terms cancel out. I phi m squared phi conjugate and m squared phi minus phi conjugate. So these two terms cancel out, and so I'm just left with I phi partial squared phi star partial t squared minus phi star partial squared phi partial t squared. So the only way that this can happen for our derivative for the probability density is if the probability density itself is equal to phi partial phi star partial t minus phi star partial phi partial t. And voila, there, right there, that right there is the probability density. So now we're almost at the finish line. All we have to do is recall that our guess for phi was some kind of a free particle of the form this should be just a momentum, p dotted with x. So now if I go ahead and take the appropriate derivatives, I should indeed show that the probability density is negative for the Klein-Gordon equation. So let's do that. So first of all, let's take the temporal derivative right here. Partial psi partial t is equal to, well, this right here, as we showed before, p dotted with x is what? Well, p, remember, is a 4-vector consisting of energy and px, py, pz, and x is also a 4-vector consisting of time and the spatial coordinates. So when I go ahead and take their dot product, if I'm just working in one spatial dimension x, then I have et minus xp. All right, so now let's come over here. If I take the temporal derivative, I'll pop out a minus ie times e to the minus et minus px. All right, so this is what I've got right now. Partial phi partial t and partial phi conjugate partial t will look very similar, but instead phi conjugate has a plus sign over here. So phi conjugate is plus here, plus over here. So that tells me that I'm going to pop out an IE instead for phi conjugate. So IET minus PX. Okay, so now let's just plug it in. So we have the probability density is equal to I times the psi conjugate, which is just E to the plus I PX. And I'm going to multiply it with this right here, okay? So this is psi conjugate multiplied with the temporal derivative shown here, minus IE, e to the minus IPX, okay? And then I have minus I times phi. What is phi if not e to the minus IPX? And then multiply it by the second spatial temporal derivative for phi conjugate. So that's going to be IE times e to the, let's see, e to the IPX. So that gives us, first of all, these two gives us 1. These two give us 1. So for our probability density, let me go ahead and write it over here. Our probability density reduces to I times minus IE. So I times minus IE minus IE, minus IE. So that gives us, the probability density is I times minus 2IE, and I times I is I squared, which is minus 1. So this reduces to 2E. But via Einstein's dispersion relation, E is equal to plus minus mc squared plus pc whole squared. If we're working in natural units, of course, these c's go away. So that means for our probability density, we have plus minus 2 times the square root of m squared plus p squared. And there you go, ladies and gentlemen. That shows how the Klein-Gordon equation results in a negative probability density. That's it for today.